So I wanted to give a little bit of a review of some energetics and thermochemistry. A lot of this was covered last year, but I know that since it's been a while, it might be good just to talk about some of these terms. All right, so first of all, there's two very important terms in energetics and thermochemistry. Those are enthalpy and entropy, all right, and they both sound kind of alike. First of all, enthalpy, which is abbreviated with a capital H, is the amount of internal energy that a substance has. All right, and there's a couple different forms that enthalpy generally can take. One general form that it can take is just thermal energy, which is like, for example, if this is a hot block of metal, there's some amount of energy just contained within the molecular motions of it. All right, so hopefully you remember, like, if something is, the temperature is hot, that's because there's a lot of wiggle of the particles, there's a lot of vibration, or if it's a gas, even like just how fast the things are. The word that we use is kinetic energy. All right, that's one type of internal energy that a substance can have. But there's also chemical energy. All right, if you have let's say a gallon of cold gasoline, all right, it doesn't have a whole lot of thermal energy, but it still has a lot of enthalpy because there's chemical bonds in the gasoline that can be turned into heat, all right, or energy. All right, so enthalpy is just that total amount of internal energy that something has. All right, one thing about enthalpy is that you can't determine that amount of internal energy as an absolute value. All right, so if I were to say, all right, here's a block of wood, all right, and say how much total enthalpy does it have? All right, well, it's pretty much impossible to figure that out. But what we can do is figure out how much its enthalpy changes whenever it undergoes some sort of process. All right. And notice when we're talking about this, I'm going to use the word process as opposed to reaction. All right. A process could be a reaction. All right. But the reason I'm saying process is, let's say you've just got a hot block of metal that cools off and turns into a cooler block of metal. All right. A lot of people would say, there's not been a chemical reaction that's occurred, but there has been a process. All right. But if a chemical reaction does occur, that would qualify as a process as well. And when we're talking about enthalpy changes, it doesn't necessarily have to be a chemical reaction. It's just some sort of change, whether chemical or physical, would qualify. All right. So what do I mean by the being able to measure the change in enthalpy? Well, first of all, we would measure a change in enthalpy with the symbol here, delta H. All right, delta, hopefully you realize, means change in, and H is enthalpy. All right, so let's consider let's say that this is a hot block of wood. All right, well, one thing that could happen to a hot block of wood is it just cools off. All right, and you go from a hot block to a cooler block, but where did that heat go? It was released to the atmosphere, or released to the surroundings. All right, so delta H is always the same. The enthalpy of the final state minus the enthalpy of the initial state. All right, so even though I don't know the total amount of energy that this thing has and the total amount of energy this thing has, I know that this thing has cooled off and it's given off a certain amount of heat from that process. All right, so we would define the change in enthalpy as the total amount of enthalpy that this thing has minus the total amount of enthalpy that this thing has. And even though we don't know these as absolute values, we know that the change in their enthalpy would be however much heat has been released. All right. So another example of this would be, let's say that we take that same block of wood and we burn it. All right. That's a chemical reaction. We would then be left with the carbon dioxide and water. All right. And whatever ash would be left over. So, and again, that process as well is also going to give off heat. All right. So if we took all of the enthalpy of the products, the carbon dioxide, the water, and the ash, right, and we subtracted the enthalpy of the starting material here, all right, that difference in enthalpy would be the heat that is given off. All right. So one thing that hopefully you are familiar with is the meaning of the signs. All right. If the change in enthalpy is negative, that means heat is given off. all right, and we call that exothermic, all right. So hopefully you'd realize a hot block of wood would give off heat, all right. That's an exothermic reaction, and the reason that it's negative is if you just focused on the material, all right, the amount, if you said what has more total internal energy, the cooler block of wood or the warmer block of wood, all right. The warmer block of wood has more internal energy. So if you take something with a small enthalpy, which would be this, and you subtract something with a larger enthalpy, which would be this, you would end up getting a negative number. All right, and that's why things that have negative delta H's are things that are giving off heat. All right, and the opposite is also true. If it's a positive delta H, that would mean heat is being absorbed. All right, so we'll come back to enthalpy in just a second, but let's talk about entropy. Entropy is a little bit of a hard term to describe, but essentially it measures the amount of disorder that a substance has. Okay, and the reason that entropy is important is just like enthalpy, entropy is one of the factors that will eventually determine whether a reaction goes or not. All right, so one thing that one thing that's different about entropy versus enthalpy is that it is actually possible to quantify an absolute amount of entropy that a substance has. All right, and one thing that we can do, one thing that's known is, this is one of the laws of thermodynamics. Ionic compounds that are at absolute zero are considered to have zero entropy. All right, so what would zero entropy mean? All right, zero entropy would mean it has zero disorder. It would be an absolutely perfectly ordered material. All right, so for example, if you had a crystal, a perfect crystal of sodium chloride at 0 degrees Kelvin, it would be considered to have zero entropy. All right, remember that in that crystal, it consists of this crystal lattice where all of these ions form this nicely ordered pattern. All right, so it's already a very ordered system. And the fact that it's at 0 Kelvin means that there's no molecular motion. All right, and one thing we'll find out is that when things start to have motion, that is a form of disorder that they can have. All right, so the thing about your your entropies is that they can be given an absolute amount. As an example of this, I'm going to refer you to Table 12 in the data booklet, and this is just some thermodynamic data on different compounds. All right, and one thing you'll notice about some of these, like they have this thing for enthalpy right here, and notice that's only available as a change in. All right, and the reason that we have change in is, again, it's impossible to say what an absolute amount of enthalpy that this compound would have. But notice when they get entropy, all right, they don't have a delta in it. You can actually give an absolute value for the amount of entropy that a particular compound would have. All right, so notice that there aren't any compounds in this list that are ionic. These are all covalent compounds right here. So even though it is possible to give absolute values, like an exact number associated with the entropy of a particular substance, it's still more common to talk about change in entropy. All right, so change in entropy is going to be delta S. All right, and if delta S is positive, so remember, S is essentially entropy is essentially a measure of the disorderedness or the messiness of a compound. If you have a positive change in your entropy, that means your entropy, your disorder, is going up. All right, so if it's positive, that essentially means that it's becoming more disordered over time. All right, so the important thing that you're going to want to remember is a couple of examples of what types of things would be associated with things becoming more disordered, or in other words, a positive delta S. All right. First of all, whenever a liquid or a solution is formed from a solid. All right. So remember that whenever you have a solid, you have molecules or atoms that are arranged in a relatively organized pattern. All right. So for example, a crystal of sodium chloride would be something like this. All right. And let's say that we were to melt that. All right. If we melt that pure sodium chloride, essentially you're going from this very ordered pattern where these things have that crystal lattice structure to this thing where these atoms or molecules are able to slide past each other. That would be associated with a positive delta S because the disorder is increasing. All right. Similarly, if we took sodium chloride and we dissolve it in water. So before you have your water molecules, which are essentially hydrogen bonding to each other, but you've got your crystal of salt, which is ordered in that crystal lattice structure. And I didn't draw the full lattice, but it's going to be three-dimensional with that alternating pattern of positive and negative ions. All right. And so what happens when you dissolve this? All right. Well, when you dissolve this orderly pattern of ions now becomes relatively more disordered because they're all just randomly swimming around as solute particles in the water. All right. So essentially the important thing to remember is to ask yourself, which is more ordered? The crystalline material, where it's in that orderly crystal lattice arrangement, or those atoms when they're swimming around in the water. All right, this is much more ordered over here. So in the process of things getting dissolved, overall things are more disordered than they were previously. All right. So another case would be a gas being formed from a solid or a liquid. All right, so when you have gas particles, these things are not touching each other and they're all moving around randomly. All right, there's a lot of disorder in that compared to either a solid or a liquid form. All right, so that change right there would be associated with a positive delta S. All right, one other thing that would be associated is whenever the number of moles increases during a reaction. All right, so this is a reaction that we talked about a while ago. This is actually a reaction that the reverse of it can happen. All right. So, but if we're just talking about the forward process here, all right, total number of gas particles. All right, we've got 2 total gas particles here. We've got a total of 4 total gas particles here. 1 from the nitrogen molecule and 3 from the hydrogen molecules. All right. So since there's been an increase in the number of gas particles in going from reactants to products, this direction would be considered to have a positive delta S. All right. Or you could just say that its entropy has increased as a result of that. All right. And the last type of increase would be whenever the temperature increases. All right. So whenever the temperature increases, that means that the amount of motion of the molecules or atoms has increased. All right. And there's a lot of different types of motion. First of all, you can have vibrational motion within the bonds. If this entire water molecule were to rotate, were just to spin, all right, that would be rotational motion. And translational motion is when this whole thing moves from point A to point B. So if I were to draw, say, 1 second, the water molecule's here, and the next second, the exact same molecule is right here, all right? Even if it doesn't rotate, it just moves from here to here, that's considered translational motion, all right? So all of these are types of motion that the molecules can have, and whenever the temperature increases, all of these types of motion in your substance will increase, all right? And when I say that, it's going to increase on average, all right? So these types of motions would be consistent with this material becoming more disordered, all right? It's more ordered when these things aren't moving around that much. It's more disordered when they are moving around a lot, all right? So that would be considered a positive delta S.